Is operator behaves unexpectedly with integers. Why does the following behave unexpectedly in Python? I am using Python 2.5.2. Trying some different versions of Python, it appears that Python 2.3.3 shows the above behavior between 99 and 100. Based on the above, I can hypothesize that Python is internally implemented such that small integers are stored in a different way than larger integers, and their operator can tell the difference. Why the leaky abstraction? What is a better way of comparing two arbitrary objects to see whether they are the same when I don't know in advance whether they are numbers or not?
Take a look at this. Here's what I found in the documentation for plain integer objects. The current implementation keeps an array of integer objects for all integers between -5 and 256. When you create an int in that range, you actually just get back a reference to the existing object.
Python's operator behaves unexpectedly with integers. In summary, let me emphasize, do not use this to compare integers. This isn't behavior you should have any expectations about. Instead, use equals and not equal to compare for equality and inequality, respectively. For example, explanation. To know this, you need to know the following. First, what does this do? It is a comparison operator. From the documentation, the operator's and is not test for object identity. X is Y is true if and only if X and Y are the same object. X is not Y yields the inverse truth value. And so the following are equivalent. From the documentation, it returned the identity of an object. This is an integer, or long integer, which is guaranteed to be unique and constant for this object during its lifetime. Two objects with non-overlapping lifetimes may have the same value. Note that the fact that the id of an object in Python, the reference implementation of Python, is the location in memory is an implementation detail. Other implementations of Python, such as Jython or IronPython, could easily have a different implementation for id. So what is the use case for is? PEP 8 describes. Comparisons to singletons like none should always be done with is or is not, never the equality operators. The question. You ask, and state, the following question, with code. Why does the following behave unexpectedly in Python? It is not an expected result. Why is it expected? It only means that the integers valued at 256 referenced by both a and b are the same instance of integer. Integers are immutable in Python, thus they cannot change. This should have no impact on any code. It should not be expected. It is merely an implementation detail. But perhaps we should be glad that there is not a new separate instance in memory every time we state a value equals 256. Looks like we now have two separate instances of integers with the value of 257 in memory. Since integers are immutable, this wastes memory. Let's hope we're not wasting a lot of it. We're probably not. But this behavior is not guaranteed. Well, This looks like your particular implementation of Python is trying to be smart and not creating redundantly valued integers in memory unless it has to. You seem to indicate you are using the referent implementation of Python, which is Python. Good for Python. It might be even better if Python could do this globally, if it could do so cheaply, as there would a cost in the lookup. Perhaps another implementation might. But as for impact on code, you should not care if an integer is a particular instance of an integer. You should only care what the value of that instance is, and you would use the normal comparison operators for that, i.e. ==. What is does? It checks that the id of two objects are the same. In Python, the id is the location in memory, but it could be some other uniquely identifying number in another implementation. To restate this with code, is the same as. Why would we want to use is then? This can be a very fast check relative to say, checking if two very long strings are equal in value. But since it applies to the uniqueness of the object, we thus have limited use cases for it. In fact, we mostly want to use it to check for none, which is a singleton, a sole instance existing in one place in memory. We might create other singletons if there is potential to conflate them, which we might check with is, but these are relatively rare. Here's an example. Will work in Python 2 and 3, for example. Which prints. And so we see, with is and ascendal, we are able to differentiate between when bar is called with no arguments and when it is called with none. These are the primary use cases for is. Do not use it to test for equality of integers, strings, tuples, or other things like these.
I'm late, but you want some source with your answer? I'll try and word this in an introductory manner so more folks can follow along. A good thing about Python is that you can actually see the source for this. I'm going to use links for the 3.5 release, but finding the corresponding 2.x ones is trivial. In Python, the C API function that handles creating a new int object is pylong_from_long_v. The description for this function is: the current implementation keeps an array of integer objects for all integers between -5 and 256. When you create an int in that range, you actually just get back a reference to the existing object. So it should be possible to change the value of 1. I suspect the behavior of Python in this case is undefined. Smile. My italics. Don't know about you, but I see this and think, let's find that array. If you haven't fiddled with the C code implementing Python, you should. Everything is pretty organized and readable. For our case, we need to look in the object subdirectory of the main source code directory tree. Pylong_from_long deals with long objects, so it shouldn't be hard to deduce that we need to peek inside longobject.c. After looking inside, you might think things are chaotic. They are, but fear not, the function we're looking for is chilling at line 230 waiting for us to check it out. It's a smallish function, so the main body, excluding declarations, is easily pasted here. Now, we're no C master code hacksoers, but we're also not dumb. We can see that check_small_int eval, peeking at us all seductively. We can understand it has something to do with this. Let's check it out. So it's a macro that calls function get underscore small underscore int if the value eval satisfies the condition. So what are smallnagents and smallpacents? Macros. Here they are. So our condition is if -5 is lower than or equal to eval and eval is lower than 257, call get underscore small underscore int. Next let's look at get underscore small underscore int in all its glory. Well, we'll just look at its body because that's where the interesting things are. Okay, declare a PyObject, assert that the previous condition holds and execute the assignment. Small underscore ints looks a lot like that array we've been searching for, and it is. We could have just read the damn documentation and we would have known all along. So yup, this is our guy. When you want to create a new int in the range, smallnagents, smallpacents, you'll just get back a reference to an already existing object that has been pre-allocated. Since the reference refers to the same object, issuing it directly or checking for identity with is on it will return exactly the same thing. But, when are they allocated? During initialization in underscore pylong underscore init Python will gladly enter in a for loop to do this for you. Check out the source to read the loop body. I hope my explanation has made you see things clearly now, pun obviously intended. But, 257 is 257? What's up? This is actually easier to explain, and I have attempted to do so already. It's due to the fact that Python will execute this interactive statement as a single block. During compilation of this statement, Python will see that you have two matching literals and will use the same pylong object representing 257. You can see this if you do the compilation yourself and examine its contents. When Python does the operation, it's now just going to load the exact same object. So it will return true.
It depends on whether you're looking to see if two things are equal, or the same object. Is checks to see if they are the same object, not just equal. The small ints are probably pointing to the same memory location for space efficiency. You should use equals to compare equality of arbitrary objects. You can specify the behavior with the underscore eq underscore, and underscore ni underscore attributes.
Jo, vänta Senor. Jag har sett en cybersubscribing.